You know, to build the future, we first had to do something that was, well, completely unreasonable. Today, we're going to pull apart the single most complicated machine humanity has ever built. This is the device that literally saved our digital world from grinding to a halt by taming a light that really shouldn't even exist. So let's get into it. It all starts with this number, 50,000 times per second. That's how often this machine has to perform one single critical task. So what is that task? Well, the scale of it is kind of hard to wrap your head around. Okay, so each one of those 50,000 events involves hitting a target. And that target is a tiny, tiny droplet of molten tin, about the size of a single white blood cell. Hitting something that small, 50,000 times a second with perfect accuracy, that already sounds pretty absurd, right? Oh, but it gets so much worse. That microscopic target, it's not just sitting there. It's flying through the machine at 250 kilometers an hour. That's about 155 miles per hour. So you've got this microscopic, super fast target that has to be hit with absolute precision 50,000 times a second. And the margin for error? What do you think it is? Well, according to the engineers who built this thing, there isn't one. They just don't miss. Ever. Now, this level of perfection wasn't just some ambitious goal. It was a non-negotiable requirement. And to understand why, we have to rewind a bit and look at the engine that was powering all of modern technology. See, for more than 50 years, the entire tech industry ran on a single, incredibly reliable principle. But that engine, it was about to seize up completely. And that principle? That was Moore's Law. The idea was simple. By making transistors smaller and smaller, we could cram more of them onto a microchip every couple of years. This gave us that exponential growth in computing power we all got used to. It was the predictable, beautiful rhythm of progress. But then, around 2015, we hit a wall. A hard, physical wall. The light we were using to literally print the transistors onto silicon, it was just too blunt to draw anything smaller. Moore's Law was, for all intents and purposes, dead. The problem wasn't the idea, it was the tool we were using. The process is called photolithography, and here's the gist of it. You coat a silicon wafer with some light-sensitive stuff, you shine a light through a stencil or a mask to create a pattern, and then you etch that pattern into the silicon. The whole thing was breaking down at step 2, the exposure to light. See, when you try to print incredibly tiny features, the waves of light themselves start to blur out the edges. It's kind of like trying to paint a miniature figurine with a huge, thick paintbrush. It just doesn't work. This is called the diffraction limit. Now, the solution sounds simple in theory. Just use a light with a much, much shorter wavelength to draw those finer lines. But the light they needed was anything but simple. To save Moore's Law, scientists had to find a completely new kind of light. One that doesn't really exist naturally here on Earth, and one that behaves in ways that seem to defy the basic laws of manufacturing. They called it Extreme Ultraviolet, or EUV light. And let me tell you, it was an absolute nightmare to work with. First off, EUV is absorbed by air, so the entire massive machine has to operate in a near-perfect vacuum. And you can't use regular glass lenses to focus it, because glass just sucks it right up too. It was this hostile, seemingly useless type of energy. And for decades, the world's basically agreed it was impossible. The early pioneers were mocked. Their idea was called a fish story. One scientist was literally laughed off the stage presenting it. Funding was cut again and again. For 30 years, this project was just a string of failures. But a small, stubborn group of engineers just refused to give up. They decided that if physics itself was the problem, the only solution was to fight back with an entirely new, almost unreasonable level of engineering. So first things first. Since lenses were totally useless, they needed mirrors. But not just any mirrors. To reflect these tiny EUV wavelengths without scattering them all over the place, they had to create the smoothest objects ever made by human hands. To give you a sense of scale, if one of these mirrors was blown up to the size of Germany, the biggest bump on it would be just 1 millimeter high. It's an almost impossibly perfect surface. Okay, so they had the mirrors. Next, they had to actually make the light. And to do that, they basically built a tiny artificial sun inside the machine. Hitting that tin droplet with a super high-powered laser creates a plasma that explodes at 220,000 Kelvin. That is 40 times hotter than the surface of our actual sun. And that violent explosion is what finally releases the EUV light. But of course, that created another impossible problem. The plasma cloud from the tin was so dense that it was actually reabsorbing most of that precious EUV light it was creating. The light source was essentially suffocating itself. For years, this one flaw almost killed the entire project. The solution they finally came up with was just ingenious. Instead of one massive laser blast, they decided to hit the droplet twice. First, a small pre-pulse laser hits the droplet. This doesn't vaporize it, it just flattens it into a perfect little pancake shape. Then, microseconds later, the main, giant laser hits that pancake, vaporizing it instantly into a perfect, low-density plasma that lets all of its light escape. Brilliant. So after 30 years of ridicule and failure, all of these engineering miracles were finally combined into a single, cohesive machine. And the scale of this final product, it's almost as mind-bending as the physics going on inside it. Each one of these machines is the single most expensive manufacturing tool in history. We're talking around $400 million a piece. It aligns all the different layers of a computer chip with a precision of just 1 nanometer. To put that in perspective, that's the width of about 5 silicon atoms. And to ship just one of them, it takes 250 shipping containers and multiple jumbo jets. And this timeline just shows you the incredible perseverance it took, from a purely theoretical image back in 1986, through decades of painful struggles, all the way to 2019, when the first iPhone with a chip made by one of these things was released. It took over 30 years to go from a fish story to the phone that might be in your pocket right now. And really, that brings us to the core idea behind all of this. George Bernard Shaw once said, "The reasonable man adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself." This machine exists only because its creators were profoundly, stubbornly, and brilliantly unreasonable. So here's the big takeaway. Every single advanced microchip in your phone, in your computer, in the data centers that run the modern world, it is now made using this technology. A single type of machine built by a single company, born from an impossible idea, is now the silent engine behind our entire digital civilization. It makes you wonder, doesn't it? If a handful of people could stare down decades of failure to build an artificial sun in a box, what other impossible things are we just a little bit of unreasonable